Hey students, welcome to section 4.0, Exponent Property Review. Let's go to work. In this video, we are going to read and highlight section 4.0. 4.0, Exponential or Exponent Property Review. Let me change to my highlighter here. Yellow, good. First, let's start with a review of what exponents are. Recall that 3 to the 4th means taking 3's and multiplying them together. So we know that 3 to the 4th equals 3 times 3 times 3 times 3 equals 81. I think that's important. Let's highlight that right there. So a lot of times we forget that the exponent just means we're multiplying that number times itself that many times. You might also recall that the number 3 to the 4th is 3 is called the base and 4 is called the exponent. Other reminds include that any number to the 0 power is equal to 1. That's definitely important. Any number to the 0 power is equal to 1. So 5 to the 0 equals 1. And any number is equal to itself to the first power. Any number is equal to itself to the first power. So remember that we know that every number that's given to us is to the first power, even though we don't necessarily write it. Sometimes it's easier to leave a number written as an exponent. For example, it's much easier to write 5 to the 20th instead of instead of 95,367,431,640,624. That took a minute to read. Not only is it sometimes simpler to write a number using exponents, but many operations are easier when the numbers are written as exponents. That's why we need to remember this, that a lot of times it's easier to work with the exponents than it is to evaluate them and get some big long number and then work with them. So starting off with multiplying numbers with the same base, let's examine the problem 3 to the 4th times 3 to the 4th and write the answer as an exponent. Yes, we could multiply it out as a standard form number, 81 times 81 equals 6,561. But let's keep it in exponential form to see if it's any easier. First, let's expand the problem. 3 to the 4th is really 3 times 3 times 3 times 3 times 3 to the 4th is really 3 times 3 times 3 times 3. Now notice that the only operation happening here is multiplication, and that we are multiplying the same number. That means that we could say the following. 3 to the 4th times 3 to the 4th is the same as 3 to the 4th times 3 to the 4th, which is really, there's really 8 3's there, so that's 3 to the 8th. Instead, we could say 3 to the 4th times 3 to the 4th equals 3 to the 8th. Do you see a rule that we could use to generalize this form? Let's look at another example, but this time with a variable. Y to the 7th times y to the 4th. Notice there's 1, 2, 3, 4, 5, 6, 7 y's here, and 1, 2, 3, 4 y's there. So that's y to the 7th times y to the 4th, and that equals y to the 11th. Why? Because if we count, there's a total of 11 y's in there. Can you find a rule that we can use when multiplying two exponent numbers with the same base? Yes. We can add the exponents. In other words, z to the 5th times z to the 6th is z to the 5 plus 6, which is z to the 11th. Would it be a quicker way to show your work for this problem, generalizing this? We could say the rule that we have the rule that x to the a plus x to the b equals x to the a plus b. Now, this will work with numbers. Will this work with numbers without the same base? Let's find out by looking at 5 squared times 2 cubed. Many people think that 5 squared times 2 cubed equals 10 to the 5th. But we know that 5 squared times 2 cubed is 25 times 8, or 200. And that 10 to the 5th equals 100,000. So we see that 5 squared times 2 cubed equals 10 to the 5th is not true. Therefore, we know that we can only add the exponents. We can only add the exponents when we have the same base. In fact, if asked to simplify 4 squared times 7 squared, we could either have to multiply it out as a regular number or else leave it alone if we wanted it written using exponents. A lot of times we forget that. We could just leave it alone and leave it written as exponents. And that's okay as well. So basically what we've just learned here is that when we multiply numbers with the same base, we add the exponents. I'm going to write that down up there. When multiplying, let's see if I can erase that highlight. Yep. Add exponents. Now, let's use our brain before we go into the next one. So multiplying, we added exponents. Anybody want to guess what we're going to do when we divide? Let's go on. Dividing numbers with the same base. If multiplying numbers with the same base meant that you could add the exponents, what do you think we will discover when dividing numbers with the same base? Let's find out by looking at the following example. 4 to the 7th divided by 4 to the 5th. Notice there's 1, 2, 3, 4, 5, 6, 7, and 1, 2, 3, 4, 5. Okay, 4 to the 7th divided by 4 to the 5th. Note that since only multiplication and division is happening, 5 of the 4s in the denominator will cancel. They will actually become 1, since like 4 over 4, that equals 1, right? So we consider that to cancel. Cancel, 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 cancel. So we're left with 4 times 4 over 1, which is 4 squared. Let's look at one more example by using variables before generalizing the rules to divide exponents with the same base. Q to the 6th divided by Q squared. 1, 2, 3, 4, 5, 6 Q's on top, 1, 2 Q's on the bottom. We can have 2 of them cancel out. It leaves me with 1, 2, 3, 4 of them on top over 1, which is Q to the 4th. It looks like our rule is similar to multiplication of exponent numbers with the same base, but this time we subtract the exponents. This gives us the general rule of a to x to the a over x to the b equals x to the a minus b. For now, we'll only deal with division cases where the numerator is larger than the denominator. But think ahead. What would happen if the denominator's exponent was larger? Well, it's not going to be any different. I'm going to go ahead and put this in here for you. Let's say I had x squared over x to the 5th. It would still be x to the 2 minus 5, which gives us x to the negative 3rd. And really soon, we'll be talking about negative exponents. So you'll see what happens then. Let's get back to our reading and highlighting. A power to a power. We can also take exponents themselves to a power. For example, think of the problem 2 cubed raised to the 2nd power. Following our order of operations, we know we have to take parentheses first, which means 2 cubed is 8, and then we square it. 8 squared is 64. However, if we want to leave your answer as a number to a power, look at the following. This squared means I have this twice, 2 cubed twice. And then 2 cubed times 2 cubed gets us 2 to the 6. Again, can you see a rule here? Let's look at the example of the variable to help again. G to the 4th cubed means I have 3 G to the 4ths. And then, of course, G to the 4th means G times G times G times G times G. And I have that 3 times, which tells me I have G to the 12th. Well, how would I get to that 12 coming from all the way back there at the beginning? How do we jump all this stuff in the middle? What's that rule that we're gonna do here? Well, for a power to a power, when using the same base, we get the rule that you can multiply the exponents. So this generalizes to x to the a raised to the b power equals x to the ab. So here, 3 times 4 got us 12. Now, let's finish up by talking about negative exponents. Negative exponents. We just learned that we could divide numbers with the same base and we could subtract the exponents. We just learned it. That's important. We only examine problems where the numerator is higher than the denominator, but what would happen if the denominator had a higher exponent? Let's look. 5 cubed divided by 5 to the 5th power. We'd have 1, 2, 3 of those would cancel. We'd be left with 1 over 5 squared. Now, however, by following the rules the last time, that we could also subtract the exponents, which gives us 5 to the negative 2 power. How are those two the same? Well, since 5 cubed divided by 5 squared is 5 to the negative 2, and also 5 cubed divided by 5 to the 5th equals 1 over 5 squared, and by the transitive property, we know that these two things are equal. So we can now generalize this rule by saying any positive integer of n where x to the negative n equals 1 over x to the n. Negative exponents must be moved to other side of the fraction bar. Now, we don't really like negative exponents, so we like them to be positive, and that's one of the reasons why we're going to do that. We're going to spend a lot of time on this negative. Okay. Lastly, the negative exponent as a reciprocal. Another helpful way to think about negative exponents is as a reciprocal. What's reciprocal mean? It's where you flip it. You flip a fraction. For example, reciprocals two-thirds and 3/2. Oops. That was ugly. And 3/2. Or 5/7 and 7/5. Those are reciprocals, just as a reminder. Okay. Remember that the reciprocal of an integer is 1 over the integer, because the number times its reciprocal must equal 1. So 4 to the negative 2 means the reciprocal of 4 squared, which is 1 over 4 squared, or 1/16. Notice that 4 squared times 1 over 4 squared equals 1, proving that we have a reciprocal. One last note is that except for scientific notation, we never leave negative exponents in a solution. We don't like them. We also take the reciprocal so that our exponent is positive. Let's look at a few more examples and notice that we can evaluate the integer powers, but the variables to a power we have to leave as an exponent. Okay. For example, 3 to the negative third means I got to put it now on the bottom to get 1 over 3 cubed, which is 1/27. 2 to the negative fourth means 1 over 2 to the fourth, which is 1/16. I think you're starting to get the idea. So there is, negative exponent operations. Sorry, we have one more page. Now that we know negative exponents mean reciprocal, negative exponent means reciprocal, we can perform operations with negative exponents just like we did with positive ones. Consider the following example of multiplication rule. Notice that we still added the exponents, but we just need to write our answer as a fraction if we have a negative exponent of multiplication. For example, 5 cubed times 5 is a negative 5. We add those. 3 plus a negative 5 is 5 to the negative 2. Well, we don't like the negative, so we then have to write the reciprocal of it, which is 1 over 5 squared, or 1/25. Again, multiplying 4 to the 7th times 4 to the negative 5th. We're going to add those two exponents to get 4 squared, which is 16. Now let's look at division. When it's division, we subtract the exponents. So 5 squared minus, so it'd be 2 minus a negative 2. Well, minus a negative becomes plus. That becomes 5 to the fourth, or 625. And this last one, 4 to the negative 1, so it'd be negative 1 minus 3 gives us 4 to the negative fourth. But we don't like the negative exponent, so we got to write the reciprocal of that, which is 1 over 4 to the fourth, or 1 over 256. Finally, we can see a power to a power. We simply multiply when it's power to a power. So here we would have 2 cubed raised to the negative 2 power. Negative 2 times 3 is negative 6. We don't like the negative, so we got to write the reciprocal of it, or 1 over 64. 3 to the negative 2 power raised to the negative 2 power. Negative 2 times negative 2 gives us a positive 4, so 3 to the fourth is 81. There we are. We have read and highlighted section 4.0. Y'all have a great day.